And I'm live. That is cool. Today is 5th of September 2025, Friday. And today we will just continue what we were doing yesterday on Combinatorics. First, we have to complete the some things were left in yesterday's stream. There was Cayley's theorem, and then there was one more thing which was left, which we have to do today. And then we will do some questions on combinatorics. So let's just begin without delay. All right, what is the point of delays? Yeah, looks cool. And why do I have YouTube here? CPHB, Competitive Programmers Handbook. And we have to do combinatorics. Burnside's lemma. Yes, yesterday we saw about symmetry. Yes, so yesterday we saw about symmetry that there is a set of configurations called S, and then there is a set of symmetries of transformations G, and that set G has transformations, and those transformations are also called symmetries. Why are they called symmetries? They are called symmetries because after applying those transformations on any of the elements on the set S, maybe Cayley draw, you have a set S of configurations, and then you have a set denoted by capital G of transformations, and in this you have configurations of a system. And what can be considered a system? Let's say a configuration could be how many ways are there to construct a tree of 4 nodes. So there is this obvious way of constructing a tree with 4 nodes, and then there is, I guess, yep, this is also another way to construct a tree of 4 nodes, and I guess those are the only ways to construct, those are the only 2 ways to construct a tree of 4 nodes, because if you take, let's say, since all of these are symmetric, you can take any of these node, and where do you stick it? You either stick it here or here, which would make it similar to this thing. So there are only 2 configurations in this. And yep, so configurations are like this. You have a set of rules. For example, in this case, we had a rule that in S, we have all the configurations in which you can construct a tree of 4 nodes. That is what we have in S. And then in G, we have a set of transformations which we can apply to any of these configurations, and those transformations are also called symmetries. Why are they called symmetries? Because when you apply those transformations to any of the configuration in this set S, the resulting new configuration that you get might be the same configuration that you began with, or might be equal to some other configuration that is already in the set S. The main thing is that after applying that transformation, you do not get out of the set S. It is inclusive. These transformations just go from one to another, and yes, they just go from one to another without leaving the set S when you apply these G transformations. And that is why there is a sort of symmetry, and that is why these transformations are also called symmetries. And let's say, for an example, one of the transformations in the set G, and G is a set of transformations, not a set of configurations. One of the transformations could be you can take any node and any edge, break it from its current location, and put this dangling side of this edge to any other node or back to the same one. So what this would lead to, this transformation, let's call this T1 transformation, or S1 is also something we can call this, because this is also a symmetry. Let's take this transformation, and we began, let's say, with a configuration like this. Here we have 4 nodes. This is a tree of 4 nodes, and this is a valid tree of 4 nodes. Everything is connected either directly or indirectly, and there are number of nodes minus 1, number of edges, that is 4 minus 1, 3 edges in this. 1, 2, 3. And if we apply this transformation where we take one node and one edge and break it and then stick it to some any other edge, any other node. Let's say we take this one node and this edge and we break it out. And if we do that, let's say we do actually just we took it out and now we have it separately here. Now we can stick this dangling edge to any other node or back to the same one. If we put it back where it was originally, we would get the same configuration. But if we put this node to some other node, let's say like this, then also this thing, the resulting configuration that we get, which is different from the original one, this thing also is a tree of 4 nodes, valid tree of 4 nodes. We have 4 nodes, 1, 2, 3, 4, and the number of nodes minus 1 edges, 3 edges. So after applying this transformation, this symmetric transformation, symmetry on our configuration, what we end up is also a part of the set of configurations that we began with. So that is why it is a symmetry. That is cool. Even though it took us like more than 30 minutes to understand this yesterday. Yo, let's go. 5 o'clock. Yo. And yep. Now we have, since we saw that there are these configurations and then these transformations. If we have a configuration, let's say just like this, if we have a configuration like this, 1, 2, 3, 4, like this, and we apply the same transformation that we applied in the one above. Let's say we take away this particular node edge and we remove it from here, and now we can, let's say we stick it on this side, so we would get like something like this. But this is very similar to the one that we began with. At the starting we had this and we did the operation, the transformation operation on this node and edge, and we removed this one from here and we put it here, and this is what we get. But these two are similar. There is no difference in their structure apart from the way that I have drawn them here. There is no difference in their structure. They are basically the same thing. So when we are calculating some number of configurations, a bunch of those configurations are going to be the same thing represented in different manners. And there is a word which we can use to group all of these configurations which are of the same type. And these configurations are called orbit. The group of these configurations is called an orbit. And what we do not want to count the number of configurations in the set S. What we actually want to count is the number of orbits in this group S. And what is an orbit? An orbit is a group of those configurations which are same, like here, these two are same. So to count distinct configurations, we have to count the number of orbits, and using Burnside's lemma, we can count the number of configurations, the number of orbits, my bad. And let's see how it works. Burnside's lemma can be used to count the number of combinations so that only one representative is counted for each group of symmetric combinations. And yesterday, when we read this for the first time, this was not making any sense. But now, this is making much more sense than it was making yesterday. Burnside's lemma can be used to count the number of combinations so that only one representative is counted for each group of symmetric combinations, which means here in this set S, we have a lot of configurations, right? And a bunch of those configurations are can be grouped together. And what is the basis on which we are grouping these configurations together? The basis is that we have a symmetric, we have a, let's say, configuration, and these dots represent one configuration. Let's say I have this configuration here and this configuration here, and here in the diagram I have put them in the same group, in the same symmetric group. And why is that? That is because there is this group of transformations which tells us what are the transformations we can apply on a given configuration. And the claim is the reason that these two configurations are in the same group is that when I take some transformation, let's say there are a bunch of transformations T1, T2, when I take any of these transformations from this G group of transformation and apply it to some configuration, I can convert this configuration into every other configuration in that group. So what this means is that when I take any of these, or let's go to this group, when I take any of these configurations and apply a bunch of these transformations in any series or repetitive manner to this particular configuration, I can convert this into any other given configuration in this group. And that is why they are considered symmetrically equal, because this group is also called a group of symmetry, not just transformation, but also a group of symmetry. And why a group of symmetry? Because whenever you apply any transformation from this group, whatever configuration you end up with is also a part of this set S that you began with. You do not go outside of this set S. Therefore, G is a group of symmetry, and applying those symmetrical operations on a configuration, you can convert a given configuration into any other configuration in that group of symmetries. And I hope that makes sense. And since you do not want to double count things in combinatorics, you do not want to count these two configurations as different configurations because they can be converted into each other. You want to count them as one. So you want to count ultimately the number of symmetric groups, which is also called orbits, the number of orbits in this set S. And that is what is said here. Only count one representative. Yep. Only one representative is counted for each group of symmetric combination, right? We want to count only one thing from every group. That is what Burnside's lemma tells us. And I don't know where I can apply this, but at least it makes a little bit more sense. We haven't actually gotten to the actual formula, how this works, but let's see. C here means Catalan numbers, which we saw yesterday. Yep, Catalan numbers. And now Burnside's lemma. How does this thing actually work? That is crazy. Okay, so what is the actual formula to calculate the number of orbits in a given set of configurations and a given set of symmetric transformations? Burnside's lemma states that the number of combinations is this. Just states that, and also the fact that this is a lemma. a lemma is not proved. It is just what we use. We haven't been able to prove it or disprove it. We have just seen it work. We do not know for sure does it work for every case, but we have not been able to find a case where this thing does not work. So this is a lemma where there are n ways to change the position of a combination, and there are CK combinations that remain unchanged when the kth way is applied. Okay, where there are n ways to change the position of a combination, and there are CK combinations that remain unchanged when the kth way is applied. Okay, I think this makes sense. Here n would mean the size of this group of transformations, of this group of symmetries, n ways to change the position of a combination. And by combination, they mean configuration, same thing, just different mathematical framework. There are CK combinations that remain unchanged when the kth way is applied. What this means is if I have a bunch of, what I think this means is that when we have a bunch of transformations that we can apply to any element in our group, then CK there, K here represents one particular transformation that we can apply to some configuration in our set S, and CK gives the number of configurations that do not change, right? That remain unchanged when the kth way is applied. That is when I apply this CK operation, how many of these configurations do not change. And by not changing, it means they stay in the same orbit that they were. So, okay, they remain in the same orbit that they initially were a part of. They do not go to any other group. They do not change. They are basically the same thing. Okay. When there are CK combinations that remain unchanged when the kth way is applied. And that is just a theory. Like my interpretation of this is just a theory. As an example, let us calculate the number of necklaces of n pearls where each pearl has m possible colors. Okay. Okay, makes sense. Two necklaces are symmetric if they are similar after rotating them. For example, the necklace this has the following symmetries. Okay, if we just rotate this, well, there is the initial one, then we rotated this clockwise, then once more clockwise, and then once more clockwise. So there are four symmetries for this. Okay, there are n ways to change the position of a necklace because we can rotate it in 0 to n minus 1 steps clockwise. Makes sense. If the number of steps is 0, all m power n necklaces. Why do we have m power n? Because there are n beads or pearls, and they used the word pearl. Yep, there are n pearls in a necklace, and for each pearl, we have m possible colors that could be chosen for it. So there are in total m power n necklaces remain the same, and if the number of steps is 1, only the m necklaces where each pearl has the same color remain the same. That makes sense. That actually makes sense. More generally, when the number of steps is k, a total of m power GCD kn. Okay, okay. This thing is cool. Now that we actually have an example, this thing makes sense. Okay. So what is the problem here? In this part and in this part, what is the problem here that we are trying to solve? Let's get to it. What we have is, we are saying we have a necklace, and in that necklace there are n number of beads, right, or pearls, n number of pearls, and each pearl can be colored in m different colors. Okay, so let's, for an example, say n is 4, the same way n was Hmm, okay, uh, why doesn't this work? Okay, now it is working. So the same way that we had n equal to 4 here, let's say we have n equal to 4 here, and let's say m, the number of possible colors, equals 3. Let's say we have three colors that we can color a pearl in. One is this reddish color, pinkish color, then green, and then light blue. These are the three possible colors that a pearl can take in a necklace. Now, in a, let's say, blank necklace slate, we have our 4 pearls, and each pearl can we make all the possible configurations. 4, 4, 6. It would be 64 total number of configurations. So that would be a lot of configurations to make. And let's go with, okay, 16, 16. Let's go with 16. Let's go with, let's remove one of those colors so that we do not have a lot of configurations and I can actually draw these. So we have n equal to 4. We have 4 necklaces, or let's go with 3. 3 would be a even simpler example. Let's delete this whole thing. Let's go with 3. We have 3 possible pearls, and each pearl can be colored into 2 different colors. So our necklace is like this. It is like a triangle. Okay. And every pearl that we have here can be colored into 2 colors. So in total, we are going to have 3 power 2 necklaces, which is 9 necklaces in total. So let's actually draw all the 9 necklaces. That is a very bad drawing of a necklace. That is a better one, right? We have this necklace and we can just copy paste this one. 3, 4, 5. 1, 2, 3, 4. Now we have 9 necklaces and we can color the pearls in 2 different ways. One is this red color and the other is this green color. So let's go through all the combinations. Let's say we color all of them green first, and then we colored these two green and the last one red. This one is red. Then let's say we colored this one as red and these two as green. Then we colored these two as red and this one is green, and then we colored this one as red and these two are green. Then we colored this one as green and this one as red, and this one is also red. Then we colored this one as red, this one is also red, and this one is green. And then, are we already there? Then we have red, red, and red. Do we have all the configurations? 3 power 2, or okay, shit, this should be 2 power 3, which is 8. Yes, 2 power 3, because two possibilities here, two possibilities here, two here, two here, yeah. So 2 power 3, we have in total 8 configurations. But if we see closely, we can see that, well, this one is unique. We can see that this one, and this one, and this one, and yep, that one is unique. This is unique, but all of these are the same. They have two green colors and one red color, two green colors and one red color. So these three are the same thing. And same goes for this one, and this one. All of them have two pink colors, right? And one green color. So they are also the same. So if we count the distinct configurations, there is this one distinct one. There is no other configuration like this. There is this one. This is also distinct. And there is this group of configurations with two red and one green. And then there is this group of configurations with one pink and two green. So in total, we have four configurations that are distinct. But if we were to apply our combinatorial formula, we would get 8 because we are double counting. So Burnside's lemma helps us to see how we can just count the distinct number of possibilities and not overcount it. And that is what we have here. In total, we will have m power n possibilities in total, where this double counting is also included and remain. And if the number of steps is 1, only the m necklaces. Okay, and then they have given us a formula. They have given us how this analogy works for this formula, and let's see how that works. Speak loud. Shit, am I not audible? My OBS says it is fine. It is at like top volume. Okay, so now we have to see how this thing fits. What is this formula? We have to see what is this formula, and they are saying that this is the formula for Burnside's lemma, and I want to make sure that this is the problem that we are trying to solve with this formula, the problem of overcounting. And the claim is, using this formula, we can solve our problem of overcounting and actually get the number of distinct configurations, which is 4 in this case, right? So here in this formula, where there are n ways to change the position of a combination, and there are k combinations that remain unchanged when the kth way is applied. What does that mean? As an example, let us calculate the number of necklaces of n pearls, where each pearl has m possible colors. Two necklaces are symmetric if they are similar after rotating them. For example, the necklace this has 4 possible symmetries. Like this is the original one. Rotate this once clockwise, then once more clockwise, and once more clockwise. These are the 4 different symmetries for this type of necklace. There are n ways to change the position of a necklace because we can rotate it this many times. That makes sense. So here, if we have n number of pearls in a necklace, and in our example, we have n equals to 3, we have 3 pearls. And for this necklace, let's say 1, 2, 3, when n is 3, does not matter, the color does not matter. We have 3 possible ways to change this. Once is when we rotate it 0 times, we do not rotate this, then we rotate it once and then we rotate it twice. So when we rotate this once, what we will have is something like this: 3, 1 and 2. This is after 1 rotation. This is after 0 rotation. And now after 2 rotations, we will have something like this: 2, 3 and 1. This is after 2 rotations. So the number of pearls in this particular case of pearls and coloring them in m ways, we have n ways to change the configuration. And here ck represents the number of pearls. Ck represents the number of combinations that remain unchanged when the kth way is applied. So that would mean something like there are like 3 ways we can change the combination, we can change the configuration, and if we apply this 0th way, then how many configurations there are that do not change when we apply this, and none of them change, right? When we are not rotating, then the configuration that we have will not change. So n is 3. Let's do the summation. Our k ranges from 1 to n, and not exactly from 1 to n. I would say it goes from 0 to n. Okay, it will go from 1 to n because I guess we are not counting this initial one when we are not making any rotation. So our k will be equal to 1 and then it will be equal to 2. So we have C1 divided by n, which is 3, and then plus C2 divided by 3. Now we have to calculate the values of C1 and C2. What is C1? C1 is when we rotate the given configuration once, how many of them remain unchanged? How many of them remain unchanged? Yep, CK combinations that remain unchanged when the kth way is applied. So let's see for C1. How many of these configurations, there are in total 8, how many of them will remain unchanged? For let's go one by one. If I rotate this configuration once, this will not change because all the colors are same. This will not change. If I apply the rotation here, this will change. This thing will go there, this will go there, so they won't be the same thing. This thing will also change. This will also change. This will also change. This will also change. This will not change. So in total, we have 2 configurations which will not change. This one and this one. So I guess we can do just, we can write this C1 as 2. And I really don't know where we are going with this, but let's just suppose and check if our theory works. Now for C2, when we rotate a thing twice, how many configurations do not change? Here we have this thing will still not change after rotating this twice. This thing will also not change after we rotate this twice, and none of these will change except for this also. So only these two are going to change. In that case, C2 should also be equal to 2, and if we put them here, we would have 4 upon 3, which is not very similar to 4, the actual answer. So what did we get wrong? There is something that we do not understand here. Do not abbreviate competitive programming in description. Should Okay, in description. Okay. I will correct that. That might give a wrong impression as to what is going on here. I mean, we are talking about coloring different pearls. So Okay, so there is something that we got wrong, which gave us the wrong answer. The wrong answer is 4 by 3, but the correct one is 4. 4 is the right answer. More generally, when the number of steps is k, a total number of this. As an example, let us calculate the number of necklaces pearls here. Two necklaces are symmetric if they are similar after rotating them. For example, this thing has 4 rotations. There are n ways to change the position of a necklace because we can rotate it in this many steps clockwise. If the number of steps is 0, all remain the same. And if the number of steps is 1, okay, so we didn't consider C0. I guess that might be the case. We didn't consider C0. C0 is going to be equal to 8. Why? Because when we rotate our necklace by 0 amount, all of them are going to remain same. So makes sense. So we have C0 equals 8, and if we do C1 plus C2 plus C0, the whole thing divided by 3, the possible number of rotations, we have 2 plus 2 plus 8 divided by 3, which is 12 upon 3, which is 4, which is the correct answer somehow. Okay, how is this working? We got the right answer, but how is it working? And more generally, when the number of steps is k, a total of generally, and I think this formula is only for necklaces. Yep, this is for necklaces. When a total number of k steps is performed, then in total m power GCD of kn necklaces remain the same, where GCD kn is the greatest common divisor of k and n. The reason for this is that the blocks of pearls of size GCD kn will replace each other. Thus, according to Burnside's lemma, the number of necklaces is this. We just put this thing equal to Ck. We are saying this thing Ck equals m power GCD Kn, and we plug that in here, and for the example, in the above example, we have this. Okay, so now we have this meta level lemma equation to find the number of distinct orbits in a given set of configurations, and we also have Ck, which gives us the number of configurations that do not change after the kth rotation or transformation or symmetry, anything you could call it. And then we have this example of necklace on which we are applying this theorem. And in this particular theorem, we have said to calculate Ck, in this particular theorem, we have said Ck equals m power GCD of k and n. So the general Burnside's lemma is k goes from 1 to n, and we have Ck divided by n. This is the general formula, and in the case of necklaces, we change this Ck, replace the Ck with this formula, with this expression. So we have, and in our this particular example, our number of cases goes from 0 till n minus 1. Number of rotations, or number of rotations, because in necklace we are dealing all the transformations are just rotations. So we can say number of rotations go from 0 to n minus 1. So k goes from 0 to n minus 1, and the formula that we have is m power GCD of k n whole thing divided by n. That is our formula for this particular case. Okay, so this is the general thing, and this is what we get for the necklace case. Now, what is happening? Okay, I do have a notion of why this formula works for CK. Why can we replace CK with this? I mean, why does this give us the number of elements which remain same after we do K operations, K rotations? This, I have a notion for this, but why does this thing work? We will have to do some research for that, some chat GPT based research for that. Why does this thing work? And as to this thing, what does m power n give us? This says that we have n things, possible things that we can change into m different possibilities, dot dot dot, first possibility, second possibility, till m different possibilities. And these are first, second, and third, and dot dot dot. In total, we have n things, and we have n things which can go into m different possibilities, right? That makes sense. So in total, for this one, first one, we have m different possibilities, and these are independent. If I choose the second possibility for this first one, I am under no obligation to choose any particular possibility for this second one, possible configuration for this second thing, or you could call it node or pearl in the case of necklaces. So these are independent. Therefore, in the second one, again, I have m different possibilities. In the third one, again, I have m different possibilities. This goes on till total. We have for the last nth thing, we have m different possibilities. So the whole thing turns out to be m power n, where we have n different things which can take m different possible states. States is a nice word, states. But when we are calculating our CK function, here K is the kth transformation, and particularly in the case of necklaces. In the case of necklaces, let's say we have 4 pearls in a single necklace. Therefore, our n equals 4. And let's say our m equals 2. That is, every single pearl can have 2 different states, and these states, let's call them 2 different colors. So in total, we have m power n, 2 power 4, 16 different possible necklaces. And when we rotate our necklace by some amount, k, let's say k equals 0, then we haven't rotate our necklace. And how many CK, what does CK represents? CK represents how many configurations of necklaces do not change after applying the kth transformation. And when k equals to 0, we haven't applied any transformation. We haven't rotated our initial configuration of necklace. And when we have not done that, then all of these possible configurations, they remain the same as they were at the beginning of a transformation. So C0 for anything is just straight up in a general formula, m power n, right? No debate. And then when k equals 1, what we have is we rotate our necklace by one amount. So every block that there is, it goes to the next one. Every pearl that there is, it goes to the next pearl. It occupies the place of the next pearl, and it's next in the sense that when we are rotating this necklace counter clockwise, when we are rotating this clockwise, so every pearl occupies the place of the next pearl in the clockwise series. When k equals 1, what would be the value of ck? It should be equal to m, because without our formula, without our elegant formula of this thing, m power GCD kn, without this formula, we can see this was our initial configuration, and we rotated this once when k equals once. When we did that, and now we are asking the question, how many of the total possible 16 configurations would remain same when we have rotated this thing once? And this would be only same if and only if the color, the original color of this block equals the original color of this pearl, which also has to be equal to the original color of this pearl, which has to be equal to the original color of this pearl, which has to be equal to the original color of this pearl, because they are all taking the place of the pearl that is next to them in one configuration. Therefore, since we have a cycle, all of these pearls have to be of the same color. And therefore, how many configurations would we have in which all the pearls will have the same color? That would be the total number of possible colors, which is m. Therefore, since we have m colors, we have C1 equals m. That makes sense if we look at our configuration of necklaces. Now, in this formula, they have generalized this notion to be equal to m power GCD of kn. And my suspicion is this. My suspicion is this, that when we have, like they say right here, this thing works, remain the same, where GCDKN is the greatest common divisor of K. The reason for this is that the block of pearls of size this will replace each other. This, according to this, we can apply this. So here we are taking GCD of K and N. What is this going to give us? K is the rotation, the number of rotations that we are performing, and n is the total number of pearls that we have. And this thing only works in this example of necklace and pearls with m colors and n necklaces. This thing only works here. The CK function only equals this thing in case of necklaces and pearls. Okay. So GCD of this thing would say that this is the greatest common divisor of K and N, and this would give us blocks of pearls. This gives us blocks of pearls that are going to take each other's place. For K equals 1, GCD K equals 1 and N equals to, in our example, 4, this thing equals 1. And what we are saying is blocks of size 1 are going to take each other's place. And what does this 1 mean? What does it mean for a block to have a size of 1? A size of an integer, positive integer, means the number of pearls that that particular block has. So every block of size 1 is going to take the place of other blocks of size 1. That is why we are limiting our total sample space. So we cannot change colors within this block, right? We can change colors in this block, but we cannot change colors outside this block. What this means is that if I have blocks like this, right? If I have blocks like this, and let's say the size of one block is 3. In each block, I have 3 pearls. What I can do is change the color of these pearls inside a block to anything that I want. What I cannot do is whatever these three things have color, whatever color scheme these three pearls have, they cannot be different from this, which cannot be different from this, which cannot be different from this, because when I do my rotation, this thing is going to take this is place, this thing, these three are going to take this place, and these three are going to take these three's place, and these three are going to take these three's place. Therefore, they cannot be independently colored. These three internally is the maximum range of motion that I am allowed when I have kth transformation. So I think it makes sense for Ck to be equal to m power GCD K n, because this is our limited range of motion that we have when we are doing kth transformation. And for that limited range of motion, this is the possible number of colors we can have in that limited range of motion. So therefore, this equals this. Ck equals m power GCD. This is GCD K and N. And if we plug this into Burnside's lemma says the total number of distinct configurations you get is K ranges from 1 to N, where you take Ck divided by N. And what is N? N is the number of transformations that you can apply, and Ck is the number of configurations that do not change after applying the kth operation. That is, they are literally symmetric for the kth operation. For example, a square, right? Let's say you have a square like this, and not like this. Yo, this is a square. Let's say you have a square like this, and you copy this, and let's say you have two transformations. One is rotating the square 90 degrees, and one is rotating the square 45 degrees. And if you take this square and rotate this 90 degrees, shit, it is not actually a square, my bad. It is now a square like thing. Let's say that it is a square. Yeah. Should now it actually is a square. This is what we began with, and let's say we do this operation where we are rotating this square by 90 degrees. When we do that, delete that. When we do that, we get the same thing. This is not indistinguishable from where we began, which was this. But if we apply this other operation where we are rotating this by 45 degrees, which is somewhat like this, then this is different from what we began with. We began with something like this, and applying this 45-degree rotation transformation, these two are not the same. So we want to count them as distinct. That is the whole point of Burnside's lemma. Yep. Now what we have to figure out is maybe we can attack at the question of why this formula works. That would be nice to know. Yo, shit. For our coding and come up with the most efficient codes. Yo, yes. I guess you have to get into problem solving. And I would say a nice thing that you can do is advent of code. You can go to this website called advent of code, and my bad for not replying, but these messages are within 1 minute. When you go to advent of code, there are a bunch of problems which you can see. And for me also, this was the thing which got me excited about problem solving. So you have to get excited about problem solving. And I think advent of code is one of the best things that you can do if you want to get excited about problem solving. So I would suggest you go to this website and try to solve these problems, and develop a logical mindset. Yep. It is not black and white answer. There is no black and white answer to this question. Building project helps you in organization skills, and they develop different parts of your brains, I would say, because building projects helps you in jumping up and down the layer of abstractions. That is, when you are building a project, you say there are some big things. You say, I want to create a server, I want to create a front end. That is at a higher layer of abstraction. And then when you get down to creating a backend, you say, I need to have a server running, I need to have a database running. And when you go even below that layer of abstraction, you say, which language am I going to use for my server? Which database am I going to use, sequential or what? So when you are building a project, you are developing a skill of organization and the ability to jump between layers of abstraction. And grinding lead code is more tactical than strategic. It is more problem solving, more quick, faster, speedy, and need both the things when you want to become a good programmer. How much time do you spend on a question when you are unable to solve it? Like, how do you look at a solution? I tended to forget the problem, and the next time I attempt it, again, the same confusion. Okay, so for this, I would say, when, like, if you are asking me personally, then when looking at a question, I can generally tell if I have any ideas which I can use to solve this question. And like, it is at times obvious when you have no idea. If you haven't read about graphs, then there is no point in trying to invent a new method or algorithm to solve a graph problem. So it is better to save your time from inventing new things and instead go and read about it. And you don't just have to get this particular question done. When you are stuck on a question, you have to have the ability to solve it. When you say that you have done a question, can you do that question any time of the day? Can you do that question at the middle of the night when you do not have any time to think about it? Can you do that question at any time? Can you explain that question to anyone else who maybe does not even know programming? If you can do that, then you can say that you understand how this question is done. And if that is the level of comprehension with which you are moving forward, then there will be no confusion. And there will be confusion when you begin to read something new. For example, there was a question in which, okay, let me actually show you. CP31, there was a question at 1200 level, which I did yesterday. Uh, this one, playing in casino. Shit, code forces is down. Okay. So in this question, what we had, okay, apart from all the problem statement, the main thing was this thing. Okay. We have two variables, x ranges from 1 to n, and another variable y also ranges from 1 to n. And what we have to calculate is a function of x minus function of y and their modulus, this thing. And this thing, to understand how this thing even works, this is g of y, and this is f of x. And to understand how this thing works, it took me 5 to 6 days. But fine, it was very confusing, very confusing. It was very, very confusing for the first time when I saw this. And in the editorial of the problem where I saw this, it was mentioned as you can just solve this using a prefix as an obvious thing, something that you are supposed to know at this rating. But I got really confused about what does this even mean? But it took me 5 days, but I was able to understand this. And confusion is just going to be there. Does not matter how good you get, you are always going to be confused. I'm confused all the time. Like, I do not understand a lot of things. I do not understand how this formula works, Burnside's lemma formula works. So you can see how I'm now going to attempt to understand why this thing works. But the thing is, you are going to be always confused. You just have to be comfortable with being confused. Okay? How to start CP? You can just start solving questions, easy questions first, to start to build a mindset of solving questions, of problem solving mindset. And you can start from here. Yep. Good luck. All the best. Jarvis. And now back to why that thing works. Why does this thing work? And since we do not have like any notion as to why this would work, we are going to go to ChatGPT. I do not understand how were people like Richard Feynman or Einstein or Newton were able to understand very complex things when they didn't have AI. They had to literally go to the library and read things which were written in the books. They couldn't ask any questions to anyone. There were no people around them when they were studying. So I just the level of genius there is different. The level of genius there is totally different. And that is the language that most other people use, but there are some legendary grandmasters in CP who competitive programming who use Python as their language. And some even use Java for that. Some use Kotlin. But yeah, CPP is the language that most people use because it is low level. Yeah, that is cool. CP is uh, C++ is the language that most people use in competitive programming. And now, why does this thing work? And why is it a lemma? Wait, shit. This is a lemma that tells us something. This is a lemma. We do not have proofs for lemmas. So, okay, a guy called Burnside just said, use this formula. What is the proof? I don't know. And this just works. Let's see. Uh, what is the yep, just ask for the proof. Right. Cocky. Okay, I will not try to pronounce that. That is a nice result in group theory and combinatorics. It gives a way to count the number of distinct objects under symmetries of a group of action. Okay. When I see when since this all of this is very new to me, when I see these words, distinct objects under symmetries of a group action, I have to apply cognitive energy to understand what these words mean. And I guess after a time when I'm more familiar to these things will get easier. These will come more naturally. Studying at my BTech first year, new to coding, how many years should I give to CP? I guess how many years? When you start CP, you do not stop competitive programming. How many years do I give to CP to competitive programming? When you start CP, if you have gotten really good at CP, you are not going to leave competitive programming. That is one thing. And if you are talking about actively studying, then there is no harm. There wouldn't be a reason to just stop competitive programming because it is beneficial. You are learning algorithms, you are learning complex things, which is good, very good. There is no downside to it. And I would say just keep doing it, either as a main thing or on side. Just keep doing it because you are learning new things. That is cool. So, statement of Burnside's lemma. This is the statement. Let G be a finite group acting on a finite set X. And if we were yesterday reading this statement, this wouldn't make a lot of sense to us yesterday, but today it is making a lot of sense. G is a set of transformations. Those transformations are symmetric in a sense that whenever I apply that any of those transformations to some element in the set X, they do not go out of the set. They are still a part of the set. Therefore, they are symmetric. But they are also symmetric in the sense some transformations are also symmetric in the set in the sense that they are literally indistinguishable. The object that I get before and after the transformation are literally indistinguishable in any way. So they are also symmetric in that sense. There are two senses in which we are talking about symmetry here. For G, a transformation which belongs to set G of whole transformations. Fix G for a given transformation G. Fix G, okay, the fix G here is, I guess, equivalent to CK. Yep, G is a transformation. See, you apply the Gth transformation to X, you get X, and then the total statement, the number of orbits, the way to calculate the number of orbits, be the set of elements X fixed by G. Fixed means they do not change when we apply the Gth transformation. Then the number of orbits of X under the action of G is this, divided by the size of G, which here was N, divided by the size of G, and add, find the summation of the objects, find the summation for G, fixed G, where G belongs to capital G, the set of symmetrical transformations, or we can just call them symmetry. This is Burnside's lemma. He just said, or three people, I've heard this name. I don't know where, but I've heard this name. The key idea, we are counting orbits. That is, we are counting the number of groups that there are which do not change under symmetry. The number of groups in which, the number of groups. And how do you put two configurations in a group? You put two configurations in a group which can be converted into each other applying some of the transformations in the group capital G. We are counting orbits. That is equivalence classes. Okay, equivalence classes. Equivalence classes. I have heard about equivalence classes, but I forgot about what these things mean. So, okay, we'll look it up. That is equivalence classes of elements of X under the group action. Under the group action. Group action, one of the transformations from the group G. The clever part is to count in two ways. Way one, count pairs where G fixes X, and way two, to count them orbit by orbit. Yes, this is the thing that we were doing, counting orbit by orbit. That is the thing we did here. We found all the configurations, then we made all the groups, and then we found the number of orbits, which was 4. But here, after applying the formula, we also got 4. Yo, yep. Proof. You have proof for a lemma. That is cool. This is the set of all the pairs where the group G fixes elements. S should. Yes, that is a valid way to define S. Okay, that is also pretty valid way to define S. The group. Okay, this is the set of all pairs where the group fixes the point. Okay, count S group by group, which is this. Size of S is going to be summation of this thing. Okay, or we could count S element by element. Okay, and then rewrite the sum using the number of orbits. Yes, number of orbits is going to be orb, where orb is the orbit of x. Orb is the orbit of x. Okay, this is going, maybe this is not very complex. Okay, let's try to actually understand what this means. Where did you start and in which order did you start learning? Sort of roadmap. Mm, uh, I, first of all, when I didn't know programming and I was a retard, I took CS 50, which is a free course you can take on programming, on computer science in general. It is a course provided by Harvard for free. It is also on YouTube. All the lectures are on YouTube, and there are also practice test cases which you have to submit. You can take this. This is like highly recommended for someone who is starting computer science. You can take this. That is what I took. Should I give in as a beginner, and should I learn advanced maths for CP? I'm not learning advanced maths for CP just yet. You would know when you need to learn advanced maths. You would know when you feel the need to learn advanced maths. And how many hours? It depends. It depends. It actually depends. Yeah, it actually depends. Where do you want to go? If you want to be just fine at CP, at competitive programming, at a rating, I would say around 14, 1500, then 3 to 4 hours a day in 5 to 6 months, you should be able to reach 15, 1600 if you are beginning from zero. But if you want to go to 2000 or some higher rating, then you need to give much more time. So that is what I would say. And how does this thing works? The number of G, yep, we defined S here when we take the union of the orbits, right? That is the definition for S when we take the union of orbits. The set of all the pairs where the group elements fixes the points. Count S group by group. That is what we do in our Burnside's formula. Or we can count this individually. But how is this thing working? Gx, what is Gx? Let Gx equal to some transformation which does not change x. Okay, and we are taking the sum of those transformations for every element. For the first element, how many? That also makes sense. That makes sense. For we are doing this for every element. For every element, we are checking how many transformations there are in the set G which do not change the sign, which do not change the X configuration. So yes, that also makes sense. That also makes sense. We can go element by element, counting the number of configurations which do not change, counting the number of transformations which do not change the given current element, or we can go transformation from transformation, and then for each transformation count the number of configurations which do not change given this current transformation. Okay, so we first found out the size of the set S. Then what? Step 3. Rewrite sum over X using orbit stabilizer theorem. Shit. By the orbit stabilizer theorem, this thing equals this. Okay, so there is a theorem called orbit stabilizer theorem. Gx is some group, and Gx is a subset of the whole thing G, where when we apply any of the transformations in this Gx group on the xth element, xth configuration, this does not change. It does not change the xth configuration. It remains same. And we have size of all the configurations divided by the size of all the elements that belong to the same orbit as x, where orb x is one of the orbit of x. That also makes a lot of sense. A given element can belong to a lot of different orbits. A singular element, a singular configuration can belong to a different, to non-zero amount of orbits. That makes sense. That makes sense. Non-zero, like positive greater than one number of orbits. That makes a lot of sense. Thus, okay, and we know this, where this is the orbit of x. Orb x is the orbit of x, and we are taking its size. So orb x is giving us the number of elements which belong to the same orbit as x, and we are expecting that that number, all of those elements in the same orbit as x, will also have their gx same as they have for x. Okay, I think that is what that is the motion that we are motioning here. And we take the total number of transformations and divide it by the size of the current orbit of the current x that we are at. Okay, I do not understand why this thing works. Okay, we know what gx is, and we are taking size of gx. We know what g is, we are taking size of g. We know what orb x is, and we are taking size of orb, size of x, size of orb x. Okay, so when we take the total number of transformations and divide it by number of elements which share the same orbit as x, we get the number of, because if there are, let's say, two elements in the orbit of x. Okay, okay, let's scale draw this thing. Currently I'm in my third year. Okay, let's scale draw this thing. We have G, which is a set of transformations. Let's call them T1, T2, T3, T4, and in total, let's say we have G. This thing represents the size of this set. So there would be a transformation, last transformation, right? And we have Gx, which is a subset of this thing, a subset of this G group, which has some transformations, G3, let's say, and G7, some T7, some transformations from all of these. I say this one, and some other transformations. And we have one of the configuration X. And the claim is that when we apply any of these transformations on this X, what we get is X. When I apply this, for example, T1 configuration of this on this element configuration, T1 transformation on this configuration X, we will get back X. That is the definition of Gx. And now there is the notion of orb X. What is orb X? Orb X is also a set of configurations. Say these x5 something. This is a set of some configurations. And the claim is that applying some combination of some of these transformations onto any configuration in this orb X set, we can convert them into each other. And now the main claim is Gx, size of Gx equals size of G divided by size of orb X. Why? Why is this thing? This is the total number of configurations. This thing. This is the total number of configurations. This thing. And this thing is the total number of configurations. Okay, I messed up. This is the total number of transformations. This is the total number of transformations. And this is the total number of transformations. And then this is the configurations which share the same orbit with X. And this is the count of those configurations. And Gx is the count of this set, which is a set of transformations which do not change X. Let's say orb X, let's say size of this thing is 2. That is, there are, for example, x1 and x2. These two are transformations in the same orbit. What this means is when I apply some of the transformations, some combination of these transformations, available transformations from the set G onto x1, I can convert x1 into x2. And when I apply some combination of these transformations onto the configuration x2, I can convert x2 into x1. So that is cool. And this says if I, okay, let's say for any given configuration in this set, we have only 2 configurations. And for any given transformation, let's say we have 4 possible transformations. For these, if I apply this T1 transformation to x1, either x1 remains same as it is or it changes to some other thing. Same for T2. T2 also either changes it or x does not change. And same for T3, same for T4. What does this end up with? This should also be true that every single transformation is coupled with the opposite transformation. For example, if I have a transformation of 90 degrees rotating something counterclockwise, then it has to be coupled with a transformation of, let's say, either performing 90 degrees anti-clockwise or 270 degrees clockwise. So these two transformations cancel this one. So the claim is that these transformations can be divided into 2, where these two cancel each other out. So if I apply T1 on this and T1 changes x1 to x2, so when I apply the opposite of T1, let's say it is T4 on x2, it should change to x1. And now let's say we have T2, and when I apply T2 onto x1, let's say x1 does not change, x1 remains as it is. So if I apply T2 on x1, since it is the opposite and there is no change, so no opposite remains the same thing. So x1 remains x1 and same for x2. So somehow we have that size of gx is going to be equal to size of G, the total number of transformations and orb X size of orb X, which is what? Which is the size of the orbit for the element X. And this thing works. I guess it is just going to take us some time to comprehend why this thing works. So I guess we can leave this satisfied. We have at least some notion as to what problem this lemma is trying to solve. And we also have a particular example on which we can work. Yeah, cool. I guess we can leave this at that and move on the Cayley's formula, whatever that is. Yo, yo, what's up? How are you? I am studying, I was studying Burnside's lemma, which gives us to find a way to count the number of orbits in a given set of configurations, which also has a complementary or which also has a set of transformations G, which could be applied on that set of configurations. And that must mean something. We have a set S of some configurations, a bunch of configurations, and we have a set of G, which has a bunch of transformations. And each of these transformation can be applied to some configuration on the set X, and they just either change to some other configuration or remain same after applying this transformation T. And so a bunch of these configurations actually are not different. We have direct combinatorial formula to find the total size of this set S, but the thing is a bunch of these configurations are the same. After applying these transformations, they turn into each other. So we do not want to count them as different configurations. We do not want to double count. We want to count them as a single thing. And this group in which we can convert any given configuration into any other given configuration, given a set of transformations. This group is called orbit. So our main goal is to count the number of orbits. I think that might make sense, not mate. Yeah, now we can move on to Cayley's theorem. Yo, same thing. Blew my mind. Yesterday, yesterday it did blew my mind. Yep, we are reading about things like divide by G and stuff, crazy stuff. I mean, I don't even think this is going to be very useful for me till I get to a very higher rating in competitive programming. But anyways, we are playing here. And this thing, I don't even know what this problem this is trying to solve. Let's see. Okay, we are moving on to Cayley's formula. Cayley was a scientist. Cayley was a mathematician. And we have at some point in earlier stream, we have talked about Cayley. If you remember, when we were discussing totient function. So, who gave the name of totient function to it? That would be Sylvester, J.J. Sylvester. And if you search J.J. Sylvester, contemporaries of J.J. Sylvester, J.J. Sylvester, what do you see? You see Arthur Cayley, same person, Cayley, Arthur Cayley. That is cool. That is cool. And I have seen that there's a person in the Discord server who has the same name as Sylvester, even the spelling is same. I don't know. That is kind of cool reference. Yep, this contest will be after a while. Yep, I have practiced a few problems. Yep, me too, me too. I actually want to get a good rating on this contest. Yep, this contest is going to be cool. I think it is Division 2. Wait, it is down. Code Forces. It is up back. Okay, cool. It was down, I guess, 10 minutes ago. Div 2. So yeah, it's going to be cool. 3 hours. Pretty cool. Code Forces. Yep. Yep. Huge. Okay, what is the time in Australia when these contests take place? Yep. That would be cool. That would be cool. That would be cool. And if you do, then could you please send the link? I would like to watch. Shit, wait. AM is in the middle of the night. Shit, that is bad. That is bad. Yes, and you should stream. It would be really fun to watch someone else. Yeah, midnight is crazy. Midnight is crazy. From 12:35 to 2:25. That is crazy. And yep, I will be very excited to watch your stream. It will be really fun. I will talk to you and chat. That would be cool. And Cayley's formula. Wait, ICPC. ICPC prelims. You are practicing for the prelims in South Asia Pacific. That is cool. And yesterday, yep, yes, yesterday was the ICPC World Cup. In that, you said in Discord that it is starting in 1 hour, and I watched it. It was like very fun. People were talking in their regional languages and they were discussing problems like crazy. And I guess three people get a single computer and they have to work on a single computer and find the solution. That looked very fun. A guy was eating a burger. Shit. L and F. I don't know. I don't know. Oh shit. In yesterday's, I haven't seen the questions. Okay. I haven't seen the questions actually. ICPC 2025 World Finals problems. Where can I see them? Problem A, all problems. Okay. Question 1, graphs. Shit. Why am I afraid? Question B, blackboard came intentionally left. Okay, let's read B. It seems short. To help elementary school students understand the concept of prime factorization, Aisha has invented a game for them to play on the blackboard. The rules of the game are as follows. The game is played by two players who alternate their moves. Initially, the integers from 1 to n are written on the blackboard. To start, the first player may choose any even number and circle it. Okay. On subsequent, on every subsequent move, the current player must choose a number that is either the circled number multiplied by some prime number, okay, or the circled number divided by some prime number, okay. That player then erases the circled number and the circles that newly chosen number and circles the newly chosen number. When a player is unable to make a move, that player loses the game. Okay, either a multiple or a factor. I've been given n, whether it is better to move first or second, and if it is better to move first, figures out a winning move. Okay, when I have 5 numbers, it is better to move 5, because only possible choices for even numbers are 2 and 4, right? How often do you look at editorials? If I'm getting stuck, wrong answer, or TLE, I just leave the problem for later after a few tries. I can tell when I do not understand a problem, and there might be something that I do not know about, maybe some factorial thing, some prefix summation to skip to get rid of TLE error. In that case, look at the editorials and do not feel bad about looking at the editorial. The whole point of the editorial is so that you can solve the problem later, right? Whenever the same concept emerges, you can solve the problem. So do not feel bad about looking at the tutorials. But when you do look at the tutorial, make sure you understand the thing which you were lacking before. Heap stuff, problem 1. I'm very bad at trees and heap. I'm very bad at heaps. And I intend to change that in this book. Algorithms, Introduction to Algorithms. There is a whole chapter on heap sort. And okay, and yes, I will go through this, and I will do a stream in which I will be writing a heap library, some sort of heap library, which does all the functions that are supposed to be done on a heap, that are supposed to be done by a heap. And yeah, on a stream, I'll do that on a stream. But before that, currently I'm reading about binary search trees, BSTs. And I guess tomorrow I will do a stream in which I will write a binary search tree. Yep, that is cool. And this problem, let's actually solve this one, not just theorize. A person can choose even numbers, and yes, since there are a lot of problems from A to B is hard one. Shit. Since it's so there is no particular order, like generally A is the easiest and then they increase in difficulty. Yep, thank you. Have a nice day. So I think there is no order in ICPC about the difficulty. Shit. So when I looked at this question, you are saying it is a difficult one, but the first impression is that this is easy, and but this is hard. So maybe you might give a lot of time to this, even though it is very hard. L was first solved. Okay, so L was the easiest then. That makes sense. So this is actually good. Okay, I have not solved questions from ICPC contests. Okay, but I will now start solving them too. That is cool. And about this problem, 2, 3, 4, 5. When n is 5, we have two possible choices. And given this choice, the second person can choose either this or this. Wait, 2 is a prime, 1 is a prime. And if given 4, the other person would get to 2. And this would be raised if 4 was chosen. And yeah, if 2 was chosen, I guess, no, 1 is not a prime. 1 is not a prime. 1 is not a prime. 2, 3, 4, 5. If you go with, if the first person chooses 2, then the next person will choose 4 and cut 2. Then the next person cannot choose anything. So second is cool. And 2, 3, 4, 5. If the first person chooses this, the second person can choose 2. This would be cut, and then the next person has no choice. And we can do this choosing because since this is an even number, right? This is an even number, which is composite, except 2. Every even number is composite. You can divide that number by some. Wait, shouldn't No, if you have like 6, if you choose 3 as the next, if you choose, what was the rule? On every subsequent move, the current player must choose a number that is either the circled number multiplied by some prime or divided by some prime. Okay, so we take 6, divide it by the prime number 3, we get to 2, we cut out 6, now we have 2 circled, 3, 4, 5, then the only possible choice is 4, you go with 4, cut 2, now you have no other choice, so going first one chose this, second one chose this, first one chose this, so going first was good when n equals 6. Okay, like you are saying it was hard, so I guess I can get back to Cayley's formula, combinatorics. Yep, let's get back to Cayley's formula. You want to pick a prime number. When I multiply that prime number, when I square or take the double of that prime number, it is greater than n. It is not always possible, I guess. The biggest prime factor, let's say for a chosen number, if our chosen number is 12, if our n is 12 and someone chooses 12, then the biggest prime number is 3 that divides this, and it is just 6, which is lower than n. Okay, I don't know, I'm just theorizing. Okay, let's get back to this. I will get to these things, and also I have to catch up on that question about choosing numbers from 1 to n, where the next one has to be a multiple of the last one. b1 multiple equal to b2 less than equal to b3, and 1 to n are the only possible choices. And now to Cayley's formulation. Let's get to this. Cayley's formula states that there are n power n minus 2. Shit, that is a formula I've seen for the first time. N power n minus 2 labeled trees that contain n nodes. Labeled trees 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And two trees are different if their structure or labeling is different. That is crazy. Next, we can see how Cayley's formula can be derived using proofier codes. I don't know what proofier codes is. What Cayley just said this. Okay. And proofier code. Proofer code is a sequence of n minus 2 numbers that describe a labeled tree. The code is constructed by following a process that removes n minus 2 leaves from the tree. At each step, the leaf with the smallest label is removed, and the label of its neighbor is added to the code. Okay, so here we will have 4 as our first number. Then we have two numbers for 2. I guess 4 again, or maybe 5, because 5 was not added. 4 again. Then we remove 3. Why do we? Wait, first we remove 1 and add 4 to the code. Okay. Then we remove 3 and add 4. One of the leaves, the smallest leaf. Okay. Then 3 is the smallest leaf. We add 4. So we have till now 4, 4. Let's predict the whole thing. We would have 4, 4, 2, 5. We have 4, 4, 2, and why don't we have 5? Finally, we remove 4 and add 2 to the code. That's the proof it. Okay, we just remove n minus 2 nodes. Okay, you can construct a proofer code for any tree, and more importantly, the original tree can be reconstructed from proofer code. Hence, the number of labels of trees, and this the number of proofer codes of size n. What would be the number of proofer codes for size n? That is some stuff. I guess I won't actually be needing this for some time. I, for now, actually just want to solve some questions. Let's do some CACS. You cannot, you have to pick a number that divides the chosen number. Yes. Let's do some mathematics. Joseph's query. Shit, only 5,000 people have been able to do this. Okay, let's begin with an easy one, just to get used to the maths. And this seems to be the easiest. 25,000 exponentiation. Okay, what is the question? Your task is to efficiently calculate a power b modulus 9. Note that the task, we assume that 2 power 0 power 0 is 1. Okay, that is easy. We can do the half exponentiation method. But before that, let me go to the washroom and I will be right back. And when I come back, I'll write the question for this, the solution for this. Yep. And by the way, Tame Impala released his new song, Loser, Mr. Kevin Parker from Australia. And let's do this. CSES, what is this? Start this question. CPP. 8. Okay. We have, how's the input given? Input, the first line contains an integer n, the number of calculations. The number of calculations. After this, there are n lines, each containing. Ah, okay, okay, okay. How to raise this to the power of this. Okay, cool. Then, and yep, n can be taken. Okay, cool. Now, 1e9 plus 7, that is prime and long. Let's create our own pow, long a, long b, and if b equals, if not b, return 1. If b equals 1, return a. Wait, what? LL is not. Substitute LL with long global. and else. Now we will also have a map. A map would be nice. Map of pair is going to be a key pair to long long. And yeah, now now if a if memo dot count wait, increase the size dot count for a b, then return memo a comma b, and if not, then ll does not mean anything. Long long, let's say x equals power of a raised to the power of b by 2, and return x into x into was b odd. If b was odd, then multiply this by a, otherwise by 1. And before I return, wait, I need x equals x into x. Yeah, I need x equals to this thing. And put this into the memory. Memo a comma b equals x, return x. And yep, for int I equals 0, I less than n, I plus plus. Long long, even though I don't have to take long long, we can just work with normal integers a and b. C out power of a raised to the power of b with a new line. And also I messed up a little bit right here. We have to make sure after this, take the modulus and yeah, x multiplied by equals, if b was even, if b was odd, this thing is odd. If b was odd, then multiply by a, otherwise multiply by b. And then take the modulus again, which does not feel very good, but anyways. And return the modulated value. That does work, but let's see. Okay, is there some problem with this? Is there some problem with this? A and B, I also have a map, which is very good. The only problem that I think could be is I'm doing this modulation 2 times, which might be bad, like slow. Let's see. Documents, programming, combinatorics programming, CSS, maths, exponentiation, C++, 20, submit. Okay, and it fails. Time limit exceeded. Okay. The memo, because you only have one converging recursive call. This one, because I'm making this call only once. That makes sense. I thought memo might be useful when I have some similar values of A and B later in some other test case, because there are multiple test cases. But time limit exceeded. I guess memo. Okay, let's try to do this without memo then. Maybe creating that map and then checking and updating is taking time. That is taking time. Okay. Oh, is it multiple? Yep, there are multiple test cases. I thought it might make it faster, but okay, it actually makes it slower. That is kind of strange. Okay, we are getting the right answer now. Hmm. I guess the time that it would unordered map. Yeah, unordered map. Yes, we can use unordered map. What? How does map differ? The map differs on pairs, and in the pairs at first location we had now the map is gone. In the first location, this thing would be A and the second thing would be B. I think this is not very we will not use this very often, I guess, because what is the chance of getting the same A, and then what is the chance for getting the same B? I guess the cost of maintaining the map is higher than the time that we would save. Map uses BST, binary search tree. Yep, red black trees. And unordered map uses hashing. You have to define a custom operator if you want pairs for hashing. That makes sense, right? Hashing, because that is the key. Okay, we got this. For hashing, yep, it, if we do use unordered map, yes, I think this is fine. And if we do use unordered map, I would have to define my own comparison function for hashing, not my own hashing function, I guess. I don't have to provide my own hashing function because C++ knows how to compare pairs, but it doesn't know, not comparator. It, it knows how to compare pair, but hashing function, shit, okay. I would have to define my own hashing function. That is crazy. Anyways, let's move to the next question in this. I've done this one. Let's go to exponentiation second. This might be the place where we have to use that. Okay, ABC. Can't we use the same thing? Okay, this will use some maths. I mean, of course, math. What does this essentially mean? A power B power C. B power C is something. I guess this would depend on the order. I could first find this and then find this. Yes. Or I could first find this and then find this. I think first finding B power C is cool instead of first finding A power B. A power B would give us a big number, albeit it will be an integer. And this should be fine because every time we are dividing B into 2, so this would take log B time to calculate A power B and for a certain B. And then if you find the power with C, then multiply this by log C. Wait, not multiply, but plus. So this is fine. First we can find A power B and then we can find that raised to the power C. And yep, I will write the whole thing again. I won't copy paste. 9 plus 7 and long long power long long A, long long B, and if not B, return 1, and if B equals 1, return A, and now long long x equals power A comma B by 2, and now return x into x multiplied by, was B odd? If it was, multiply this by A, modulus 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 multiply otherwise with y1, x equals x into x. Now x mod with m, and x equals x, or x multiplied by equals, depending if b was odd. If b was odd, then multiply this by a, otherwise by 1, right? And then return x. 5 int n c in n for int I equals 0, I less than n, I plus plus, long long a b c. Now in a b c, and let's say b equals power a comma b, and then c equals power b comma c, and c out c with a new line. At least it should be correct. That was my thought, but clearly not. So there is some mistake. Shit, there is a particular order. There is no hash function for pairs a power b power c. So I cannot do this thing and then whatever this thing is, let's call it x power c. I have to first find b power c. Shit. Okay, let's also see the reason. 2 power 3 power 4. That actually makes sense. Does it? Wait. This is 81. 2 power 81 and 8 power 4. This is 2 power 81 and this is 8 power 4, which is 2 power 3. Now into 4, which is 2 power 12, which is not equal to 2 power 81. That makes sense. So it is right associative. Uh, b equals power b raised to c, and then a equals power a raised to b, the updated value. Okay, I think that was the main thing here, that these are right associated. Hey, thank you for that. Yo, good morning. How is it? Shit, it is 3 o'clock there. I guess not even 3 o'clock. You are up very early. And how was your hackathon? You were very excited for it. Shit, is it taking... Wrong answer is crazy. B raised to the power of c. Then whatever we get, the new number that we get. Wait, is it because of the modulus somehow? think it might be 3:50 a.m. Hey, pretty early. It's not even 4 o'clock. But this thing does not work. Since I'm taking modulus, okay, let's talk about mod 5. Mod 5. 0, 1, 2, 3, and 4. And if I have a number whose modular representation is this, and if we multiply this number, whose modular representation would be this? 6's modular representation would be 1 mod 5. And if we multiply this number with a number, we are multiplying this number with itself. Yes, we are multiplying this number with itself. But how many times? I guess with 6, it is always going to remain wherever it is, since mod 1 multiplied by itself is just 1, and with 2, it will go to 4. When it is at 4, 16 mod 1, it will always go around in cycles of 2. Shit, that looks like the flag of Morocco. That is how it goes. And I have a raised to the power b raised to the power of c, and wrong answer is crazy. It is because we are taking mod of b power c. B power c, we cannot just take mod of b power c. Hackathon was wild. I was nowhere near the coders that came, but grew many connections. That is cool. They appreciated that I am in 11th. Yes, that is very appreciable. Participating in such a competitive hackathon, and I learned new technologies. That is very cool. The prize money was awesome. It was 30k. Shit, 30k is a lot of money. 20k for second, 12k, which is awesome. Yes, I could have won, lol, but it was cool even. Yes, I suppose it was very cool. Shit, there was a lot of money involved. Okay, so this is pure maths. This is pure maths. A power B power C. And if I take modulus of this thing, let's say I have 7. 7 is represented on the modulus wheel of 5. It will be represented. This is 1, 2, 3, 4. 7, a number like 7 will be here. And let's say I want to raise 7 to the power of 7, right? But what I am doing actually is we are taking mod of 7 with 5 before, and we get 2, and we raise the number 2 to the power of 2 to the 4, and we get to this, which is actually correct, because 7 raised to the power of 7 is 49. 49 mod 5 is also 4. That is correct, but it's still, it doesn't give us the right answer. Is that the mistake there, or something else? B raised to the power of c, then whatever b becomes, we raise a to the power of b. It's shit, everything is gone. Let's go with 5 again. 0, 1, 2, 3, 4. And at a, we want to find a power b power c. And a equals 10, let's say, let's choose just any random numbers. And c is 3. 20 to the 20 raised to the power of 30, and whatever the result is, we are going to raise 10 to that power, which is 1e 20 power 30. So on this modular wheel, should all of them give 0? Answer, and yes, answer would be equal to 0. So that is bad. That is bad. Let's say 7. 7 would be here. Hmm. 49, 343, a power b power c. There is something with modulus arithmetic that I'm missing here. A power b power c. Yep. What's up? An expert came from NVIDIA and Microsoft, and I am so obliged to get a talk with them. So, got to know this experience and knowledge, what stuffs are happening in real world scenarios. Yes, I mean that is very fun. That is very fun. You got to meet a expert who came from NVIDIA, who genuinely works in the real world, and you got to have a talk with him. So that is cool. And shit, I said talk with him, assuming the gender. Talk with them. You had a talk with them. That is cool. Mhm. A raised to the power, raised to the power. And yep, what we are trying to calculate here is we have a bunch of numbers A, B, and C, and we want to find this thing. And our direct formula of calculating this is not working. So we are trying to theorize. And yes, I feel like I might be able to come up with something, but maybe not. Let's see. There are also no editorials for CACS problems. That is one thing. Let's check what the correct method is for the question that we did earlier. Okay. A simple way to calculate the power of A would be just to directly multiply, right? Such a solution requires OB time and would be too slow because B is 10 power 9. However, we can create a more efficient log B time solution using the fact that this thing equals that. Yes, we know that for sure. Yes, we know that for sure. When B is even using this formula, it suffices to calculate this only once and reuse the result. Recursive. Power A, B, comma, M. M is the modulus. Yo, yes, yes, yes. We can provide the M. Yep. B equals 0, the answer is M. 1. Yep. Otherwise, we first calculate P equals this. And yep, lower bound. If P is even, the answer is P square. If B is odd, P square into A. Mod M. Okay. And if B is odd, multiplied by A and take mod M, then return P. Iterative solution. We can also implement the algorithm iteratively, which is more efficient in practice. Okay, the following code goes through the binary expression of B and stores the corresponding powers of A in F. That is for each power of 2k, F is equal to 2 AK2. Raise this to the power of this. P is 1 mod M. Okay, so we want P to be equal to 1. And we have long F equals A initially. While B, if B is odd, P equals P into modulus P equals P into F. F is this. The following code goes through the binary representation of B. How is it going through the binary representation of B? We are taking AND. The one, is it odd? If the last bit is odd, if the last bit is 1, then multiply. Otherwise, F into F, just square this thing. And then right shift. This is basically right shift. F is to power K. Okay, K is going forward from 0 to the highest power in B, that is storing a bit. References, CPL algorithm, binary exponentiation. Okay, we have B as a binary number. If the current bit there is 1, we multiply P, our answer, by F, and if not, F is equal to this thing. Yes, F is equal to this thing. We are multiplying F by itself every time and taking modulus by M. And so we would have that makes sense. And then we are right shifting B. What does this thing work? If we have 3 raised to the power of 5, which would be 81 into 3 to 43, right? That is 4. We would have 243. Now you say we represent 5 in binary as 1 0 1, and we start with F equals 3, and we have our product equals to 1. Yeah, we have our product equal to 1. When we see the last bit, it is 1. So we multiply P by F, which is 3. So P becomes 3. When we get to the next bit, it is 0. But whatever the bit is, when we multiplied P, or maybe didn't multiply P, when the current bit was 0, we multiply F by F itself. So it became 9. Then we saw 0. So we don't do anything. Then we multiplied this by itself. It became 81. And now we saw a 1. So multiply this by this, which is correct, 243. What would this mean in terms, in mathematical terms? Uh, yes. P should be equal to A power B. And we are splitting B equals 2 power something. Here we have B equals 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. That is what we are writing B as. So P equals A power 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. Okay, and then we split like atom, we split, and here we have 2 raised to the power 2 power 2 multiplied by A raised to the power of 0, which is just 1, and then A raised to the power A raised to the power of 1, which is actually nice. Okay, which is actually nice. Yep. And yeah, okay, and here we have 2 power 0, 0 into 2 power 1, and at any given point f equals this part, and this part we get from B. That makes sense. That makes sense. NVIDIA, the winning team, a direct interview opportunity, which was cool. Oh, okay. Think of it this way, a raised to power m modulus a equals a. So if b raised to a power c is a multiple of m, you should raise a to the power of 1 and not 0. A raised to the power of m modulus m equals a. That would be 0. Returns a. Okay. My modular arithmetics is bad. Okay. So if b raised to the power of c is the multiple of m, is a multiple of m, and then I take modulus with m, I will get 0. Wait, so we are just nullifying a raised to the power of m modulus m equals a. So if b raised to the power of c, a raised to the power m modulus m equals a, this would be when this thing, wait, a raised to the power, why is this very familiar? M minus 1, is it 1? A raised to the power of m minus 1 modulus m. Should, why can't I just understand this? Okay, this thing modulus m, Fermat's little theorem. No, it should be 1 here, and m minus 1 a raised to the power m minus 1 modulus m. M is prime. M is prime. Right. For any coprime x and y, x raised to the power y modulus y equals x. ATS theorem, that's it. You ATS. What is ATS? Fermat's ATS theorem. equals 1, and if we multiply both sides by a, which we, yeah, we can, yes, shit, okay, okay. This would only be true when a is less than m, I guess, and yes, we will get that. Yes, now I understand this bit, why this thing is true. And Fermat's little theorem only works when a and m are coprimes. A, this is Euler's. I am very dumb. Modular arithmetics, and here we have this thing, x raised to the power m minus 1 equals m. You multiply both sides by m by x, we get 1 for totient. Don't look at the totient function yet. I think I'm muddling things up. That is true. And since that is true, and wait, where m is a prime and x and m are co-primes. So in our case, m is a prime. In our case, m is a prime. Yep. And if a and m are co-primes, if I raise a to the power of m mod m, we get a. That is true. The multiple of m. If this thing is a multiple of m, okay, then you should raise a to the power of 1 and not 0. That makes sense. If a and b are, if b raised to c is a multiple of m, could it be a multiple of m? It could only be a multiple of m if b equals to this thing, because we are only multiplying b by b itself. And if it is a multiple of b, I'm just being too dense here. If this thing a b raised to the power c is a multiple of m, x m, then x m, we take modulus by m, we can rewrite this as a m modulus m x. This is in multiplication. I'm just being too dense here. And you are doing your best to explain to me, but I'm just being too dense and I'm not getting any of this. Okay, let me see. Yes, this part I do understand. A raised to the power of m, and thank you for being patient and trying to understand me and trying to explain me. Thank you for that. and m modulus m equals a, and okay, I can figure it out. I can figure it out, and I I can figure this out why this thing is whatever it is on my own. And thank you for you trying to explain me. I do not want to like bore you with me being dense. Consider this example. If 3 raised to the power 5 remainder 5 is 3, yes, so you cannot take mod 5 in the power. 3 into 3 into 3 into 3, mod 5 is 3. This is if this thing is 21, 1 is the answer, and yes, I cannot take mod 5 in the question. Shit. I cannot take mod 5 in the question. Yes, I cannot take mod 5 in the power. That makes sense. I cannot take mod 5 because 3 power 5 is 81, and if I take mod then I get 1. But if I take mod in the power, I get 3 power 1, which is 3 and is not equal to 1. Okay, so a power x into m, and then I take mod, I will get the wrong, I will get 1 because this would become 0. I'll get 1. But 1, no, 1 power, so I will get a. But should, yes, yes, I will get a, I will get a, I will get a. But a is not right. A is not right. Yep. You basically have the idea. So you take the mod 1, mod minus 1 for the power. Answer should be b equals mod minus 1. Okay, so we can just change the mod like that because we want to change the mod in the two. Okay. So for a power b power c, and if we are writing this as a mod m, and here we have taken b power c mod m, this could give 0, and we are just trying to change this mod with this so that we don't have the same thing here. We can do I'm just being very dense here. Okay, let me first of all update this function so that it also takes m, and when it takes m, we will take modulus with that given m. all the function with the m, and here you are saying that for this thing give m minus 1 and here give m. Hmm, I don't want to submit this. I want to create some examples in which I will understand how this thing, why this thing is working. And yep, so this is what the stream is for, so that I do not chicken out. A power b power c, and we have mod m for this thing, and then we have mod m for this thing. I guess yeah, I guess I can watch some YouTube videos on this, and that would clear something. You are saying that I'm very close to it, but thank you for your optimism. Yes, and yep, I will submit this when I get this on my own. And thank you for helping me here, pointing that out. And now I can look it up after the stream because I cannot watch YouTube videos on the stream. Copyright. Counting divisors. Let's try to do that. Given n integers, your task is to report for each integer the number of its divisors. For example, if this, then this. Can we just, that would be easy. I can use sieve at first. After this, n each line x. Hmm, that sounds easy. Let's see a C boilerplate. And yeah, what do we have? Void, not sieve, but we would have a vector of int fact, and yep, range equals 1e6 plus 1, right? That is the maximum value. Yep, 26 plus 1, void fill facts. Not fill. Why would I don't need the factors themselves. I only need the count. And the size is range. And facts for 1 equals 1. 1 has only one factor, that is itself. And then for int I equals to I less than range I plus plus, facts I plus plus, because the current number is also a factor of itself. And let me initialize this with 1, because every number is a factor of 1. For every number, 1 is a factor for that number. Now for int or long x equals to into work for int x equals 2 into I, while x is lower than range x plus plus, x plus equals I, and facts x plus plus. This current number is a factor. I is a factor of x. Fill facts, and then C in N, and for int I equals 0, I less than N, I plus plus int C, taking C and C out, facts C. I think that is correct. Okay, that is. And could there be a mistake? Nah, this feels right. We're counting the number of factors, and yeah, this is kind of like push forward dynamic programming, whatever that is supposed to mean. Counting divisors, C++20. Yeah. Okay, cool, cool, cool. That does work. Oh, at least one question right, and I'll be right back. I have to go to the washroom. I'll be right back. Yo, yo, I am totally back. We got that right. Let's see the analysis. Solution 1. The following solution count returns the number of divisors for x. It checks every integer k between 1 and root x. If k is divisible by, if x is divisible by k, we found 1, and I guess we increase the count. Yep, yeah, k goes from 1, while k square is lower than x, lower than equal to x. Yep, because x could be a, yeah, and if k is not equal to, yeah, if k is not a root of x, then only then increase this for the other side. Okay, that is a naive thing. The solution works in a similar manner to the sieve of Eratosthenes. It creates a vector count that will contain the number of divisors for each number x between 1 to n. Creating the vector takes n log n time because the total number of steps is bounded by the harmonic sum. Yes, this sum. The notion is this. This the solution works in this time. That is fast. Okay, so how do they do this? For j, yes, add I, j starts at I. Hmm, you do start with 1. Okay, I start with 2. That is fine. Cool, that is the same thing, basically. But I do want to write that other approach for this one. Instead of pow, long, long, and we have f equals a initially, and then while b, what we do is if b is odd, then res multiplied by res equals res into f, and we take modulus with m, and for every step we multiply f multiplied by f, and f mod equals m, take mod with m, and b left shifted by 1. Yes. B left shifted equal to 1. Return res. This should also work, hopefully, or maybe not, or maybe not. Res equals res into m. F is increasing, being multiplied by itself. Cool, now it works. It was the solution for this one. Let's submit and see if this one is correct. Submit. Cool. And yeah, more maths questions. Common divisors, sum of divisors. See this one, common divisors. You are given an array n of n positive numbers. Okay, your task is to find two integers such that their GCD is as large as possible. The largest n square is the straight up approach that comes to mind. The first input number line is this, and okay. Hmm. I cannot find GCD for all the numbers, for all the possible pairs. Maths, that is maths, maths, maths. But I didn't realize my maths was this bad. I knew it was bad, but GCD, they need to have factors in common. Common divisors, they need to have divisors in common. I can find the number, not the number, but divisors for all the numbers. I can create a matrix. Yes, I can create a matrix. But then how do I find the two vectors which have the maximum overlap? Wait, shit. Is it binary search? GCD is going to be equal between 1 and 10 power 6. Yes, that is the maximum value, 10 power 6. Is it binary search? For a given particular GCD, I can divide all the given numbers with this, and if at least two of them are divisible by this, then this is cool. Then my answer is either to the right or monotonically decreasing function. So I have to find the greatest value of this GCD where this GCD divides at least two numbers here. Finding this GCD takes log n time, and inside each operation I can take n time, so total time complexity and log n, which is feasible. Shit, okay. Binary search, and we will have a function which will return boolean is GCD. It will take a vector of integers reference to that take and int GCD, and what it will do is bool p equals, initially let's say it is false, or wait, return false, and inside I will run a loop. C equals 0, and for int x in a, if no remainder, when I divide a by GCD, then C plus plus. What is A? Right, X. If C greater than equal to 2, return 2. C in N, and now the vector, which is vector int A size N for auto X, A, C in X, and after I have everything, int L is going to be 1, and R is going to be 1E6, and while R minus L is greater than 1 and R plus 1, R is never the answer. R is never the answer. L is always GCD. R is never the GCD. So int M equals L plus R minus L divided by 2. And now if is GCD for vector A, this M, if this is GCD, and since L is always GCD, then L equals M, and if it is not the GCD, then R equals M. See out L, because L is always the GCD. Hmm. Answer should have been 7. Shit. Ooh. Okay, of course. It is not a monotonic function. Shit. If a given number returns true, if a given value of GCD, let's say G for this function, returns true, that gives us no indication as to what G plus 1 would return. That was stupid. That was stupid. That was stupid. Okay, so binary search is not here. I thought, shit, that is a genius idea. But no, that is not a genius idea. That is completely wrong. GCD. I do not want to find. Yep. I wait. If I go and I check, I divide all the numbers with 2, and I see that none of them, or like maybe just one of them, is divisible by 2. That is, 2 could not be the answer. Then every number that is divisible by 2 is not going to be the answer. Then if I go to 3, cool, and I can skip those numbers. I think that works. After taking in the input, we create a vector of integer of Boolean GCD size n, initially true, and then int mx equals 0. Now for int I equals 0, I equals 1, I less than, what is the maximum number? Makes, again, okay, let's say I will go up to 1e6 and I plus plus. Now, if not GCD I, or I, if not GCD I, then continue, but even before that, if I greater than the maximum value in, what is the maximum value in this here? Int mx initially is 0 and mx equals maximum of x, and mx I have the maximum value, and mx g as in GCD, and this will go up till equal to mx, and I don't need this. If not this, then continue. And now for the current number, bool p equals false. Now for int x in a, if no remainder when x is divided by I, if this is divisible. If not p, then p equals true. Else if p is already true, then break. And here, what if there is only one divisor? Makes sense. So I need a count. C plus plus. If c greater than equal to 2, break out of that. for loop, and if c greater than equal to 2, then this is possible. Then mx g equals I, because this is possible. Said this is bad, this is bad, this is bad. No, no, no. This might not actually be bad. For int x equals, for int x equals else, else. If this is not the GCD, then every multiple of this thing is also not going to be a GCD. So for int x equals I, or 2 into I, while x is lower than mx, lower than equal to mx, and x plus equals I. What we have to do is GCD x equals false. CDMX. I don't know. I don't know. It doesn't even work. Why doesn't this work? Hmm, this should have worked. 15 is the maximum, so that is correct. And at the end, C out, C space, and I space, new line. Why didn't I go further than this? Not GCD, because we begin with 1. No, no, 1 should be fine. 1 should be fine. But with yes, this does not make sense. Why do we get out at 3? Okay, not going to 4 makes sense, but why did we not go to 5? Who made 5 equal to false? C out GCD. Clang, no, no. Why is it very small? Why is it this small? N, because not N, but MX. MX plus 1. Okay, yeah, yeah. Okay, at least we are getting the right answer. Here, I will go at max for mx times. Yep, I will go mx times, and for every possible GCD, if the current I is not a possible GCD, then we continue. The only concern is time complexity, not the correctness of the algorithm. Let's see how that actually goes. CP competitive programming and submit. Hopefully this works. This is common divisors. Common divisors. This is common divisors. Okay, my bad. Counting common divisors, not counting divisors. Okay, that was the only concern. At least the algorithm is correct. Only we are getting time limit exceeded error. Yep, we are getting time limit exceeded error, which is bad. Can we fix that? Nah. Okay. Shit. I'm just unable to solve questions. And it's only been 3 hours and I feel tired. Let's quit whining. I'll do at least one more question. One more question at least. And in our thing, we were able to like, no, we do not understand why Cayley's theorem works, but we do understand what it gives us. It gives us n power n minus 2, the formula. But we do understand what this thing is, Burnside's lemma. Yes. My brain just feels fired, and it would be much better if I just take a break and then get back to studying. Yep. Equals 1 if I is a factor of some number. Yes. Yes, that makes sense. That I would be equal to 1. But then I would have to go through every I from 1 to the maximum possible value of I. And for every I have to divide it with all the numbers in the array to figure out if it is 1 or not. Is that the thing? And you can group numbers by their factors. I feel very bad because I'm just looking at the solutions that you are providing me. I feel like very, very bad because of that. Yeah, shit. Yes, I feel very bad just looking at the things you are telling me the answers. That is bad. I want to become a good programmer. Shit. Profair code. Profair. And yeah, I guess my brain is just not working right now. Maybe I drank too much coffee and I'm being dense. And for today, I guess this would be the end of today's stream. And thank you for being here. And especially thanks to you, Eric, because you have helped so much in today's stream. Thank you for look at this. It is just fan number 1. It says fan number 1. Yeah. Thank you for being here today. And today, this would be the end of the stream. Thank you. Bye.